My great pleasure to introduce Aleksander. Alex is a researcher at Amazon. He was a PhD student at Caltech, working with John Maxwell, and a postdoctoral fellow at Perimeter prior to joining Amazon. Alex will be moving to Yale to start faculty positions himself. Those of your client of postdocs and grads and grads. Alex has done a number, the leader of quantum information, and has done a number of interesting work on fault tolerant quantum computation. And in particular, part of the work that I find very interesting is the bridges that Alex tries to make between many body theory and error correction. And so,
thank you, Benita, for a very nice introduction. Hello, everyone. My great pleasure to be here, and I'm very surprised, positively surprised by the turnout today. It's really hope that I was not distracted. So today I would like to tell you a few words about how we can reduce the overhead of quantum error correction more than a quantum computation. So we would like to have quantum computers. We are building them with components. So, in order to have reliable, scalable, we use a method of fault tolerant and quantum error correction. So here's how I see the fault tolerant quantum computation, where we start from going to components, but then we do clever techniques to put them together in a way that the resulting machine can run arbitrary quantum algorithms, and the outcomes are the ones that we. So first we start with some physical systems, for instance, superconducting, and then we understand what are the negative operations that we can realize. So for instance, in superconducting qubits will be NIH neighbors. And of course, the qubits of an NIH are imperfect, and however, if the imperfections are low enough, then we can start using clever techniques of quantum reflection and fault tolerance, and as a result, we can obtain logical qubit and logical state with far superior volume and physical qubit, physical world. And at this point, we can forget about the underlying hardware. We don't have to worry about the intricacies of physical system that we use to realize our computer. We just think abstractly of qubits, gates that are perfect, and with them we can have algorithm, for algorithm. And at this point, I would like to stress that useful quantum algorithms oftentimes require of the order of a billion or more objects. So therefore, if we want to run them reliably, and even with the failure, error rates be something like 10 to the minus 10, which is very, very small. So this is the reason why we believe that the method of fault tolerance will be resistant when we do quantum computation. In order to move along this path of fault tolerance, we have to solve many problems, and it's not easy to move along this path. And I do that. I will be focusing on mostly on the middle part of it, the error correction. And here the challenge has many facets. So one is we have to identify good. So here I don't define what good means, but I mean good quantum error correction codes that will desire for properties. But then this is not enough. We have to know how we can use those codes. We need to have a classical decoding algorithms that allow us to operate those codes. Then this is still not enough. We need to be able to implement logical operations. And lastly, me as a theorist, this is like the easiest problem to solve. We need to realize those codes with the hardware. In reality, that's the biggest challenge, of course. But all those components can be individually optimized, and if we put constraints, for instance, on the data, we may be having a hard time realizing certain quantum error. And when we move along the path towards fault tolerance, one of the main roadblocks that we need to solve if we are to build computers is to reduce the overhead of reflection. It brings me to the overview of my talk today. In this talk, I will be talking about two simple methods how we can reduce the qubit and time overhead. So I will start with a very brief overview of the QC basics. I know that the topic is fairly diverse, and many of you know those topics, but some of them may be less familiar. So in order to be sure that we're on the same page, I will further discuss the arguably the most important factor, the historical and the decoding problem. So this problem is very well motivated because if we cannot solve the decoding problem efficiently, there would be very little hope. And then I will proceed to the first part of my talk. And in the first part of my talk, I will be talking about the greater qubits. And so in this part of the talk, I will try to convince you that it pays off if we realize that in the lab we have more than just qubits and Pauli nodes. If we take a little bit deeper, there are quite a few gains. And in the second part of the talk, I will be talking about the single shot quantum fraction. And so here, so irregular qubits will help us with reducing the qubit overhead. A single shot quantum fraction will help us with reducing the time overhead of quantum computation. And here, if we pick our code properly, we would be able to handle measurement errors without the need to repeat measurements. So let's get started. So this intro is very so the Toric code is this famous code that can be defined on a two-dimensional lattice or square lattice. We will take qubits on the edges of the lattice. And then the code space is defined as the +1 eigenspace of parity checks. Parity checks are commuting Pauli operators that we measure. And there would be X-type parity checks, Z-type parity checks. X-type parity checks are associated to vertices of the lattice, and they're reported on all the qubits on edges incident to that vertex. Z checks are supported on plaquettes, and they are acting on qubits thermometer. So this is the code. The code by definition is +1 eigenspace of all parity checks. So this is a CSS code. So when we think about handling errors, we can think of handling X and Z errors independently. So for simplicity, I will focus on handling Z errors. So let's assume that we have a state in the code space of the Toric code, and now some Z errors affected the state. So the adversary applies Pauli Z onto those qubits, but we don't know that. But what we can do is we can measure parity checks. We measure the parity checks. Then they will give us +1 measured outcome because we can use the error. And the state that we start with was by the +1. However, if we measure now X parity checks, some of them will not commute with this error, and they will give us -1 measured outcome. And this is what we call the syndrome. The syndrome would be all the parity checks that gave us -1 outcome. In the Toric code and in other topological codes, the interpretation of syndrome is very nice. We can think of Z errors as strings and the syndrome as the endpoints of those strings, as depicted in the figure here. You have this light blue string of Z errors, and the only information that we have about this string is its endpoint. And those are the X parity checks that don't commute with error. So now notice that you may have different strings with the same endpoints. And so what we would like to do is we would like to identify what errors happen in the system. Luckily, we don't have to identify the errors exactly. And we have to identify them only after stabilizing. So what it means is if there's an error, the light is there, and that's the system, and now our correction is the dark layer. And if those two guys are combined, they're actually of the logical space is trivial because those two operators combined form a stabilizer, which is a product of two shaded packets. Those stabilizers stabilize the logical space. They're actually the logical space is trivial. So that's good. So we don't have to identify the errors exactly, only after stabilizing. But of course, you know that there could be errors that are inequivalent, and if we were to apply a correction identified by the dark blue color, we would implement the logical operator and our correction fail. And so the coding problem now can be stated as follows: for the query code, given the syndrome, our task is to find a recovery operator that is equivalent in the sense of equivalent after stabilizing to some zeros that have a system. So there are efficient solutions to the coding problem for the query code. For instance, many of you heard about the minimum further. Here, the idea is that in the query coding problem, what we see is an even number of point-like syndromes, point-like excitation. Think of them as excitation. And now what you want to do is you want to pair them up in some particular way. With minimum matching decoder, you pair them up in a way that the total weight of the correction that you apply is minimized. And this will, the interpretation of this decoder is that it finds the most likely error. It's not an optimal decoder because an optimal decoder will find the most likely error. But this one is finding most likely the most likely equivalence causal errors. This one finds the most likely error. But that's you know in practice this is a very good decoder. This is how it works. Of course, there could be some further improvement of this. Okay, so far I was not involved in any noise structure, but in realistic settings, we may have some noise bias. So for instance, when we have photonic features, we may have, for instance, either significantly greater than X and Y errors. Okay, so now notice, so we consider the same example that I started on the previous slide. We have some toric state and now some Z errors up. And those are the likely errors. And then now if we measure Z checks, they do not provide us any information about this this dominant noise. So could we improve that? In particular, what we would like to do is we would like to tweak our error correcting protocols a bit, but not much. We don't want to come up with a new layout of the qubit. We don't want to come up with a new fault-on architecture. We just want to do a small tweak in order to exploit the knowledge of bias. So can this be done? Well, it turns out yes. There are simple tweaks. So for instance, instead of measuring a priority check of Z type, we could measure priority check of Y type. And this very simple idea is a powerful one, because in this very configuration, instead of only getting the syndrome that is the endpoint of the string, we also get those priority checks flagging, giving us -1 measurement output. And this would increase, roughly speaking, sensitivity to the dominant noise. And this idea, can generalize to in the code. For instance, we can apply a single qubit Clifford operator to locally change the basis, the Pauli basis, which we have, and in order to benefit from the noise bias. And if we apply this this very simple rationale to, for instance, the 3x3 circuit code, we can see significant gains. So what I'm plotting here is, so this is the 3x3 surface code layout. And on the x-axis, I list all possible realizations of the 3x3 surface code where I allowed for arbitrary single qubit polygon, single qubit Clifford operation in like qubits. And on the y-axis, what I plot is the logical error rate for that code. So what we can see is that the discrepancy between the best performing realization of the 3x3 surface code and the worst performing realization of the surface code, this discrepancy spans towards the function. So with this seemingly very naive knowledge, we can get significant gains. So can we exploit some other notifiers as well? So this brings me to the first part of my talk, which is the idea of erasure qubits. So one noise bias that is quite present in quantum technology, in many quantum technologies, is the bias between the amplitude damping errors and the phasing errors. And typically, the amplitude damping time is shorter than the phasing time. So, what is the amplitude damping noise? Typically, to encode a qubit, we use two states that differ in energy. So now the amplitude damping noise captures a process, a relaxation process from the excited state to the ground state. And that happens with probability gamma. And if you want to see the amplitude damping noise at the quantum channel, it's operators. Not K1. And so amplitude damping noise turns out to be more benign, so to say, than the polarizing noise. And that applies randomly Pauli X, Pauli Y, Pauli Z errors. And this is exemplified by two things. So first, in order to correct, like in this case, approximately, in order to correct any single amplitude damping error, it suffices to consider a 4-qubit code. If we want to correct any single Pauli error, we consider a 5-qubit code. So we see that we get away with fewer qubits. And then the second illustration why the amplitude damping noise is slightly more benign is that the surface code threshold, like we're talking about code capacity threshold for the amplitude damping noise, is around 40%, and this should be contrasted with the code capacity threshold for the polarizing channel that is around 19%. So indeed, there's a reason to believe that amplitude damping noise can be beneficial for quantum characterizing protocols. So the question now is, how can we leverage that? So it turns out that there exists a very simple encoding, a so-called dual rail encoding that can be beneficial. So the dual rail encoding uses 2 qubits to define 1 qubit, and to define our dual rail qubit, we will use the subspace spanned by state 0, 1 and 1, 0. So now, when there is the amplitude damping noise acting with the same strength, independent on both qubits used to realize the dual rail qubit, its action will be with probability 1 minus gamma, nothing happens to the state, and with probability gamma, the state is mapped to the state 0, 0. Importantly, the state 0, 0 is orthogonal to the qubit subspace. So this is just the definition of the erasure channel. So you can think parallel erasure. So you can think of the erasure channel as a channel that with some probability 1 minus gamma does not affect your qubit, and with probability gamma, there is some classical flag, or equivalently a state orthogonal to the qubit subspace that you can check. So then you know that your qubit is there. A erasure channel and a leakage are very similar. You can think of erasure channel as leakage that you know Okay, so here's basically the idea of erasure qubits. So the dual rail decoding is a realization of the idea of erasure qubits. And the idea behind erasure qubits is very simple. We want to, so we have some physical system. Now we want to realize, we want to define the qubits within this physical system in a way that the effective noise that acts on that engineered qubit is erasure bias. So the dominant noise is erasure. So let me show you a very simple example to illustrate that corrective erasure is significantly simpler. So we will go back to our good old friend, the word code. So now what we think of, what is depicted here is the locations of erasures. And those are the dark blue lines. So some erasures happen, and importantly, we know that they happen there. So for simplicity, I can think of an erasure channel as a channel that applies randomly identity X, Y, or Z with equal probability at each location where the qubit is erased. So I know where this happens. And so now if I measure for instance, the X party check, I can observe this syndrome. And so if some erasures happen, I am not guaranteed any particular syndrome configuration to happen, and any syndrome configurations that are adjacent to the erased qubits are equally likely, and they can happen. So this is a configuration of the measurement outcomes that can happen among many. So let's assume that this happened. So if I know which erasure qubits, where the erasure qubits, what I can do, and this is the optimal strategy, is basically to move those point-like syndromes to one point within each connected component of erased qubits. So in my case, it would boil down to, say, for instance, I could choose to move all point-like stations to this one. I would move this guy here, and that guy there. And this would correct this error perfectly. However, if I didn't know that those are the locations where the qubits got erased, I could be tempted to apply a correction that is depicted by a light blue edge. And in that very case, we'll make a logical error. And so one can ask what is the error correction for erasure errors, and it turns out to be very high. We know that it's 50%, and we know it by mapping the decoding problem for erasure errors to a subnet problem that is a bond calculation problem of balance with our two products. And so, of course, in the system we can also have Pauli noise on top of erasure errors. So now, what we would be doing is we could apply the same methods as discussed previously for the minimum encoder or belief matching or unifying, to name a few. And for the expert, what we will be doing here is we will be adjusting the edge weights for those decoders and incorporate our knowledge of erasure errors. And what we can do with those decoders is we can consider a noise that comprises erasure errors with probability P and Pauli noise with probability P, say phase noise with probability P. And then we can study what is the correctable region in the E-P plane. And so the y-intercept will correspond to the threshold for the phase flip noise, which in this case is around 10.3%. The x-intercept would correspond to the threshold for the erasure noise, which is 50%. And all the points here would correspond to error strength, where we can handle those errors. And this would be the practical region. So basically, by scaling up our system, we would be obtaining and here you just a lot of that. So what we did in our work, we just considered the noise model, the circuit noise model, and with parallelity ratios and polynomials. And here we assume the standard circuit noise, where each component can fail the property TP. And then on top of that, we also had possibility that handling gates erase both qubits, and this happens with property TE. And here we assume that we know exactly where those erasures happen. So, for instance, for some particular value of erasure noise, we plot the logical failure rate as a function of the Pauli error rate for different code distances. We see the intersection. This tells us that the threshold, the p threshold for in this case is around 3 times 10 to the 3. And we can do that for different values of p and t, and that way we can interpolate we can find out the boundary of the correctable region. So what I'm depicting here is again the EP phase space in the correctable region for the standard protocol, where we don't use the information about erasures. This is the dark color, and the light color, which is our protocol that does use information about the erasures. And as you can see from this plot, the correctable region increases quite a bit, in this case by a factor of 55. And of course, what I told you here is that the assumption that I made is that we know where erasures happen, and this is a realistic assumption. Our erasure detection may be incorrect. So there would be some false positive and false negative erasure detection rate, but you shouldn't worry too much, because you can still use those numerical results to figure out how well our protocol will work. It turns out that false positive detection is more detrimental, because this is a situation when the environment fools us that this qubit got erased, so we think that it got erased. So then what we would be doing is we would be reinitializing this qubit. So we would be the ones doing the erasure. So with this simple argument, we can convince ourselves that roughly speaking, having false positive will boil down to increasing the erasure rate. The false negative are less detrimental, and false negative basically boil down to increasing the Pauli error. So what's the punchline of this slide in the numerical study is the rule of thumb for the target noise rates that we want to have is we want to be sorry, we want to be deep in the correctable region. So the target noise rates should be erasure rate of the order of 1%, Pauli error rate of the order of 0.1%, and false negative, false positive erasure detection of the order of 1%. So we also studied how the sub-threshold performance of our protocol compared to the standard protocol. So the two lines that we should be comparing are the blue lines. The solid one is our protocol, and the dashed line is the standard protocol. And so we see that our protocol significantly outperforms the standard one, and our protocol also can outperform standard protocols, but when the error rates are reduced compared to the erasure protocol. And this can be exemplified by yellow and green line. Okay, so at this point you can be thinking, wait a second, is the comparison that you're doing apples to apples? In particular, to realize an erasure qubit, you use 2 qubits. So you could use those 2 qubits to build, say, the bigger surface code. And that's a very good point. But the life is more complicated, and namely when you talk to experts, they will tell you that, for instance, if we think about superconducting circuits, having two so a transport that is used to define qubit, this is not a component that takes a lot of room on your chip. So what we envision is having a erasure qubit that comprises two transpons and one readout resonator, whereas in the standard scheme we would have one transpon, one readout resonator for one qubit. So of course there would be some penalty, there would be some increased chip size with our erasure scheme. However, the increase would be mild. And so we are pretty much comparing apples to apples. And an important point is that with the erasure scheme, so now assume that you have n transpons that you can use to realize whatever you want. And with n transpons and erasure scheme, you would be able to realize a smaller surface code than for the standard scheme. However, you will be able to correct up to root n/4 erasure errors. With the standard scheme, you'll be able to correct only up to root n/8 unknown powers. So here you basically win in two different ways. So first, the threshold for erasure error is higher. And second, the exponent, how the logical error rate suppressed is higher as well. So you win the difference. So at this point, I hope that I motivated you that there are significant benefits of using erasure qubits. So now an obvious question would be how to realize it. So a natural setting in which erasure qubits can appear and were considered is neutral atoms. With neutral atoms, we would define a qubit based on some metastable levels in such a way that gate errors and take us to disjoint subspaces that can be monitored. Their population can be monitored. So if our qubit, if our state is a qubit, something we will know about. But we can realize the idea of erasure qubits also with superconducting circuits. And for instance, we can consider coupled microwave cavities, or as we considered in our experiment, we can have two resonant. And in all of the approaches, the underlying idea is basically we leverage detectable leakage. So our state goes to some other subspace, and we can detect that. So in our case, it would be leaving the qubit span subspace and going to the 0, 0 state. So in order to apply the rationale from the previous slide, we need to have an experimental realization, and that meets two requirements in erasure qubits. So the first requirement is that we better have a large erasure bias that is defined as the erasure rate to the rate of all other errors in the qubit substance. And the other requirement that hardware realization of erasure qubits needs to meet is the ability to detect erasures without further compromising our encoded qubit, without introducing errors on the erasure qubit. So in our experiment, we demonstrated that indeed the dual rail encoding with superconducting qubits can meet those two requirements. So in order to establish that we do have a large erasure noise bias, what we performed is a single qubit randomized benchmarking experiment interspersed with frequent erasure checks, as depicted in this graphic. And what we see is that the erasure rate per Clifford gate was the order of 4 times 10⁻³ and post-selective node erasures. We obtained that the residual error rate affecting the qubit subspace is at the at the level of 10 to the minus 4. So this demonstrates that we have a large erasure noise bias, and the bias is of the order of 40. And in order to verify that we can perform erasure checks efficiently and they don't compromise the quality of our qubit, what we first did is we analyzed the false positive and false negative erasure detection rates. So in the experiment, we prepared the state either in the qubit subspace or in the 0-0 state, and then we performed an erasure check followed by the measurement of the state. And this allowed us to estimate the false positive and false negative rates to be around 10 to the minus 2. And lastly, we analyzed what happens if we perform repeated erasure checks within some fixed evolution time. We varied the number of erasure checks, and we saw that the phasing induced on the qubit by the erasure checks is below 10 to the minus 3%. So what's the punchline of this slide? The punchline of this slide is that performance that we saw with this part of the realization is already compatible with the QEC targets on the erasure qubits that we discussed in these 2 slides. Okay, so with this, I would like to go to the first part of my story. Now let me talk about the second part of the story, where we talk about using the handbook. So I'm not fully explicit about it in the previous part of the talk, but quantum error correction is itself a noisy process. And for instance, in order to measure parity checks, we need to run some short circuits, that comprise state preparation and time gate measurements. All those components are noisy. And so in the process of measuring a parity check, if we're not careful, we can introduce new errors, more errors, correlated errors to this. So we have to be careful what our solutions are. So in particular, the problem that we discussed, the decoding problem for the Torah code, becomes unsolvable if one of my measurement outcomes is wrong. But now I have odd number of points, so I cannot master. But don't worry, it's not that we cannot solve the problem. We can't solve the problem, but there is a penalty that we have to pay. And the typical approach is even if we have unreliable measurements, what we have to do is we have to repeat them many times in order to gain confidence in the measurement outcomes. And of course, then we will be able to figure out what to do, what are the likely errors. But then the penalty that we take typically is that the logical clock speed is reduced from the physical clock speed. And the reduction is oftentimes a factor of the full distance, at least for the surface code approach. So the other problem with the measurements is that we may become sensitive to time correlated errors. So there have been a few methods that allow us to operate quantum error correcting code with imperfect measurements without repeated measurement rounds. But if those methods are applied to the surface code, the 2D surface code, we will have to sacrifice the geometric locality of the checks that we measure, and also checks that we measure will become big, macroscopic big. So this is not what we would like to see in the perspective of full models. So what I will discuss in the next 3-4 slides is a different approach based on a novel topological quantum code, the 3D subsystem code. This model is capable of single-shot quantum error correction. And what it means is we can measure parity checks once, and even though their measurement outcomes may be incorrect, we can proceed with reliable quantum error correction. And with this approach, there will be no QEC slowdown. However, the trade-off that we're doing here is we're trading time overhead for space overhead. Because with this under 2D surface code, we have a two-dimensional architecture, but the third dimension is time. In this construction, we have three spatial dimensions, but then there's no time. Okay, so what is this model? I'll show you one realization of this model on the cubic lattice. So we take a region of the cubic lattice, and the volumes of the cubic lattice can be colored in red and blue. And we will place cubes on the edges of the lattice. And the structure, the model in the vault looks as follows. For every blue cube, we will have Z Pauli checks. Those Pauli checks are of weight 3. There will be 8 of them for each cube. For red cube, we will have X Pauli checks. And again, there would be of weight 3. But this time, if you look closely, you'll see that what I'm depicting, Z checks, some Z checks and some X checks don't commute because they overlap on single qubit. And you may be worried because I told you that by definition, stabilizer codes are defined by a set of commuting Pauli operators. Now I'm showing to you some non-commuting Pauli operators. But you shouldn't fear because this construction is not basic stabilizer code, it is a slight generalization of stabilizer code known as a substantive code. But I don't want to go too much into the details. And this is how we modify the boundary of the system. Right, so we discussed that parity checks don't commute, but from the parity check, I can form operators, stabilizer operators. They do commute with one another and other complementary parity checks. The stabilizer operators of this model will be identified with cubes. And if I measure those weight 3 parity checks, I can obtain the measurement outcome of the weight 12 stabilizer by multiplying either this quadruple of measurement outcomes or the other quadruple of measurement outcomes. And this is so in the absence of measurement errors, the measurement outcomes of the stabilizers would be the only information that is useful for doing error correction. So the stabilizers are the ones that tell us about the presence of errors in their neighborhood. So what's the decoding problem for this model? It's very much similar to what we discussed in detail for the 2D forward code. We can think of errors as forming string-like objects, and the signature of those errors are the endpoints. So the syndrome will be like the point-like object in blue. Okay, so this is what we see, this is what we use for error correction, if our measurements are perfect. But notice that we actually measure more than just those stabilizer operators. We measure those parity checks. So now I can also incorporate in this picture the information that captures the outcomes of those parity checks. So I'm depicting the parity checks that give me -1 measured outcomes. And so it turns out that there is some structure of those parity check outcomes. Those parity checks outcomes, the ones that give you -1, I'll call them the flags. And they have to form closed loops, as depicted in the figure. Those loops can fluctuate very widely in the system. Nevertheless, they will form closed loops. And what's the origin of how does that appear? That how do we see that those guys have to form closed loops? Well, there's a certain local relation between those measurement outcomes. And so notice that if I take the product of 2 quadruples of those parity checks, I will get the identity operator. So what it boils down to is the product of measurement outcomes of those 8 parity checks is guaranteed to give me 1. So this is like a local Z2 Gauss law, and this is how you can convince yourself that those fluxes will form closed loops. And in this picture, we have 2 fluxes, green and yellow. The syndrome that tells us about the errors is the locations where yellow flux turns into the green. So this is the story with no measurement errors, but if we have measurement errors, we will not see closed loops, we will see some chopped strings. But this is where we can leverage this auxiliary information. So now the single shot encoder, which was as follows, and in the first step, what we would do is we would see this spaghetti structure, but we would correct it, make sure that our flux is from closed loops. We can do it in some fashion. And then in the second step, what we would use is we would discard the information about fluxes, and we would only know, we would only use the information about the point light syndrome, the charges, and we would do the decoding as for the 2D curve. And both steps can be done in the very much. Okay, so I will be brief here. So you can do numerics, and you can see what happens if you do repeated rounds of quantum error correction. And in each round, what you do is you insert new errors into that system, then you extract parity and measurement outcomes, and and you use this information only from that round, and then you use the single shot minimum first pass decoding, and you repeat. So you see the threshold, and then you can ask what happens if I increase the number of QEC rounds. And we see that for this model, the storage threshold is above 1%. And the only other model that can our model be referred to is the gauge color code that also has single shot error correction property. However, the threshold for that guy is significantly lower, and the discrepancy will only magnify if we consider circuit noise. Because in our case, we measure parity checks on 3 for the gauge color code, it was to measure parity checks on 46. Okay, so let me tell you a little bit about proving that this model has single shot quantum error correction. Because so far, I just showed you some numerics, but you may be interested in knowing how one can go about and prove that this model has single shot error. So, first step, the first thing that I want to clarify is that once we have measurement errors, we will be unable to guarantee that we're back to the code space. But what we will be proving is that the residual noise that is left in our system after we apply error correction is kept under control. This can be captured by the following theorem. So the theorem says the following, that for sufficiently small parameters eta and eta captures the measurement error rate, and tau captures the physical qubit error rate. And there exists some other parameters, tau prime and delta. They tell us about the strength of the residual error rate and the increment in the logical error rate. And so for some choice of parameters, we have this inclusion, and this inclusion tells us that if we have a state encoded in the 3D subsystem code, and we apply some local stochastic noise to it, and then we do single shot decoding, then the outcome of this process can be used as a state encoded in the 3D subsystem code with some, again, local stochastic noise applied to it. And the non-trivial part about this theorem is the following. So first, the type of the noise is the same. So we have local stochastic noise, and then the outcome is also local stochastic. Notice that this is not trivial because the recovery might have done something messy. And the other aspect, the non-trivial aspect of this statement is that how the parameters scale. So basically, the residual noise, the strength of the residual noise is suppressed to 0 if the measurement error rate goes to 0. And the other interesting thing is that the increment in the logical error rate, this parameter delta, can be made arbitrarily low if we below the threshold and if we keep scaling our system. Then what we can do is we can combine the statement from the theorem, we can iterate it times, and then we will see that the residual noise is kept at bay, throughout the process, and the logical array grows linearly in the number of applications of this error correction procedure. Okay, so a couple of remarks I will skip. If you want me to comment on them, ask me later. Because in the last minutes or so, I would like to tell you a little bit about going beyond topological codes. So in the talk, I was talking about the Torah code construction and you can think about other topological codes, and they're great because they have this nice structure that we can place qubit on the lattice, and then the parity check that we measure will be geometrically local on the lattice. But there are certain limitations on topological codes. In particular, if we consider a code that is defined on some Euclidean lattice of linear space L, and this lattice is in the dimensions, then there are various bounds that can be established on the code parameters. And you'll see that in the dimensions, and the scaling of the parameters that you can hope for is the following: the number of physical qubits will scale as L to the power of D, but then the number of logical qubits will scale as L to the power of D minus 2, and the distance of the code will scale as L to the power of D minus 1. So notice that if we look at D equals 2, what can we get into dimensions is we get, n scales as L squared, K is constant, and D scales as L. And from those bounds, we see that the surface code, the toric code, which you mentioned, is basically optimal. We can have, in n qubits, we can only encode a constant number of logical qubits, and the distance would scale as root n. And in 3 dimensions, it's less clear, and there have been interesting recent developments that basically provided constructions that's happening bounds. Okay, so we see that with topological codes we get nice parameters, but we cannot get good codes. Good codes would be when we have the scaling of logical qubits to be linear in the number of physical qubits, and also we would require that the distance scales linearly in n. But from the very early days of quantum information, we know that good quantum error correcting codes exist. However, those guys would not be topological codes. And those guys would have parity checks of unbounded weight. So, they could have microscopic operators we need to measure. And this is not something that we want to do. So here's where the quantum LDPC codes come into play. LDPC stands for low density parity codes. So basically, those codes, you can think of them in spirit as topological codes, but we sacrifice geometric locality, right? So we still have parity check of constant weight. But now we cannot place our qubits on a geometric lattice and require that the operators that we measure are geometric. So quantum LDPC codes are a strict generalization of we sacrifice the geometry. So this question was, are there quantum LDPC codes that are good? And there has been a very exciting development on this question over the past couple of years, and some of the people in the audience, made breakthrough results toward answering this question. And those developments culminated in a construction of good quantum LDPC. And so, as I said, recently there has been a lot of progress on those questions, and one of the very interesting construction of good quantum LDPC is the one by Levery and Zedler, called the quantum analysis. I don't have time to define them, but very roughly speaking, those codes can be defined on an object called a left-right Cayley complex, and that object has vertices that are associated with elements of some finite group, edges, and square faces. And there you would place qubits on those square faces of that object, and we would identify parity checks with the vertices. And what are the parity checks of a quantum mechanical code? They are induced by a pair of local classical codes. Anyhow, quantum mechanical codes are good LDPC codes. So I didn't define them properly, so I cannot tell you really how to decode them. But I will try to tell you how, very truly how the idea, what is the idea between decoding the quantum mechanical code. And I apologize the experts in the audience because this is a very cool idea. So please maybe don't listen to what I'm about to say this. So through the analogy that I can give you without defining the code is, let's think about the 3D sublabatory code. It can be defined, say, on the qubit lattice. We place qubits on faces. We would have Z checks that are identified with Q, and X checks are identified with edges. And so now if we measure, and if we want to decode X errors, the problem would be the same as we discussed, string-like errors, point-like extensions, point-like syndrome. However, the decoding problem for Z errors would have a different structure. Instead of point-like syndrome, we would have loop-like syndromes. So we would have some patches, some two-dimensional patches where Z errors happen, and the signature of those Z errors will be boundary of those patches. So this is what I depict in this little cartoon here. So now the problem of torsional decoding would be, how do we fill up those loops? And it turns out that there are simple strategies based on cellular automata that work. So what are cellular automata? What are those strategies? Well, so we envision that there is some agent at each location of the lattice, and what the agent does is they look around, they look at the structure of the syndromes, and they make some adjustments. They impact some local corrections that try to remove the syndrome from the neighborhood. And then we need to iterate a couple of times, and then we can remove the errors of the system. Those strategies work. However, they are designed in a careful way, because we can imagine that if we have some careless design of those rules, the action of one agent can undermine the action of the other agent. So you have to be careful to avoid local inconsistency that local agents may introduce. Okay, so with this, I can tell you very roughly what the coder for the one-time code does. It consists of two steps. One is some local 3D decoder, and what it does is it removes the syndrome locally, but then it introduces some inconsistencies in the correction. And then there is a second step of the decoder that handles those inconsistencies. So there could be a sequential or a parallel decoder that reduces this type of inconsistency called the message. And that's basically what the quantum mechanical was. That's how quantum mechanical can be decoded. And in this analysis of Lenaly and Zeno, they look at the noise resistance. So what we do is we analyze the case with measurement errors. So what is the setting? You should be familiar with from 2 slides ago, 3 slides ago. What we assume is we have a state encoded in the quantum code, and then we have T repeated rounds of quantum error correction. At each round we have new Pauli errors, and our correction is done with the decoder from the previous slide. And that decoder uses syndrome information only from that round. And of course, there could be some measurement error that in that round. But we use the information, we proceed. And after T times, we ask what's the output. So the output can be viewed as the state in the code space with some residual error. So now we want to understand what is the structure of the residual error. So what we prove is the following. for any epsilon, which captures the desired strength, so to say, of the residual error, there exists some constant delta, such that if in each round the fraction of the qubits and the fraction of measurement outcomes that was affected is smaller than delta, and then the residual error is upper bounded by epsilon n. And so one thing is that each QEC round consists of a part of the folder with constant number of iterations. So the whole process is really done in constant time, so that's good. And an important thing to have in mind is that here you don't have any other examples of noise, so in our code it can be correlation, translation, whatnot. The only assumption that you make is the marginal. And this is very interesting because all the previous results of single reflection were either applicable to adversarial noise or local stochastic noise. So we either kind of consider like the worst case scenario or typical scenario. But in our case, with the good LPs, we think those two scenarios favorable. Okay, so this brings me to the summary of the talk, in which I was telling about two simple methods for results of computation. One was the erasure qubits, and where we have this efficient way to convert dominant nodes to erasures. And it turns out that this idea is not so far-fetched and can be experimentally realized. And the other idea to reduce time overhead was the idea of single-shot refraction, where we study an efficient method of handling measurement errors. And here I just told you about realization of this idea of topological code, or more generally with functional code. And as this solve all the problems in photon quantum computation? Of course not. For instance, with functional VPC code, we mostly probe this part of this trifecta of problems. We have construction of quantum codes, but people started to probe how we can realize those functional VPC code with hardware. And still there's plenty of opportunity to explore how to load those LEDs. And with that, I would like to thank you for your attention.
So like you kind of showed like the amplitude errors like in the ratios. Is there an equivalent thing? So there are certain classes of qubits where you can have large amplitude errors and small dephasing errors. There's other classes of qubits where you have small bit flip like errors and with the phase error. Of course, already biased codes for that, but like, are there ways in which you could convert the phasing into an erasure system? Would that be easier? And so eventually,
this would be such a recognition that we set it to phaser. So we take those here with operators.
I wanted to know which parts of this proof are decoder and code specific. So the proof where you can have local stochastic noise, a recovery operator, and determine that it's close enough to your code space. Is it what aspects of the 3D subsystem code does it exploit, or the planner code does it exploit, versus being generic tool that can be applied? And I don't know if that has a short answer. If not,
We can talk about it later, just to give you one idea. For instance, in the proof of the single shot error correction with the subsystem protocol, you do leverage the structure of the noise having loops, and then the decoder is the minimum performance decoder. this is an important part of the proof. I'm not sure how this can be removed.